All right, I'm going to show you how to solve the handout that we did or got today in class. So here goes. The properties of waves problems. This is the classwork and homework. So period and frequency. The period of a pendulum is the time it takes to move through one cycle. As the ball on the string, right, the plumb bob, is pulled from one side then let go, it moves from side to side in the starting place and then returns to its start. The entire motion equals one cycle. Frequency is a term that refers to how many cycles occur in 1 second. For example, the frequency of the sound wave that corresponds to the musical note A is 440 cycles per second, which we call 440 hertz. So cycles per second is the value that we're associating to hertz. The unit of hertz is defined as the number of cycles per second. So we're going to be using these simple equations to make sense of the handout. So a string vibrates at a frequency of 20 hertz, right? Show your work here. So what's its period? Well, the period is going to be 1 over the frequency. So 1 over 20 hertz equals 0.05 seconds. A speaker vibrates at a frequency of 200 hertz. What is its period? Well, T is equal to 1 over F. 1 over 200 hertz is 0.0005 seconds. Number 3, a pendulum takes 10 seconds to swing through 2 complete cycles. How long does it take to complete 1 cycle? Well, if it's 10 seconds for 2 cycles, it's going to be 5 seconds for 1 cycle. So what is its period? Well, its period is 5 seconds. So what is its frequency in hertz? Well, frequency is 1 over period, so 1 over 5 equals 0.2 hertz. Moving on to waves. A wave is a traveling oscillator that carries energy from one place to another. A high point of a wave is called a crest, and a low point is called a trough. The amplitude of a wave is half the distance from crest to trough. That means from here to here, or here to here. That the distance from one crest to the next is called a wavelength. So we can say a wavelength would be from crest to crest, we could say trough to trough, or we could say any location to the next point of the same location in its next oscillation. So a wavelength can also be measured from trough to trough, or any point from the wave to the next point occurs. So in the graphic to the right, the following parts, label the following parts of the wave. So I tried 2 for you. So crest, crest, trough, trough, and here we can talk about amplitude. I'll just label those A. So how many wavelengths are in the picture? Well, if I look here, I'm going to go ahead and show you that it starts here. Here's 1. Here's 2. So I have 2 wavelengths total. We're going to be using the symbol lambda to reference wavelengths. So what is the amplitude of the wave? Well, in the reading part, in the y-axis, you can be able to see, I can just label it here, 5 centimeters. So 5 centimeters is my amplitude. So there's page 1. Page 2. So now you have to do some drawing, using of the grids to draw the falling waves. You're drawing them yourself. It's probably a good idea that you get some practice with this. So be sure to label the y-axis to indicate the measurement scale. So I'll tell you right here, right now, that I have you using each square equals 0.25 centimeters. So I've created a scale here. So a wave has an amplitude of 1 centimeter and a wavelength of 2 centimeters. Well, if each box is 0.25 centimeters, you're going to find that it takes 4 of these. If this is 0.25, 0.5, 0.75, and 1. So I've already put my dots on here just so I can complete this, but I want you to see here. I think it's a good idea for you to be putting dots down so you can connect them. So I'm going to go ahead and do that for you right here, right now. And I always draw like a little horseshoe so I have a nice, clean, smooth transition. And you'll see, and they're not going to be perfect, but they'll be okay. So a wave amplitude of 1 centimeter and wavelength of 2 centimeters. That means the wavelength here is going to be 8 boxes. 8 boxes, because each one has 0.25 centimeters. So in this case, I've got 1, 2, 3, 4, that's half, 5, 6, 7, 8, that's 1 wavelength. And then here I've got 1, 2, 3, 4, 5, 6, 7, 8. So I drew my second wavelength. So I satisfied the rules here. So in a different color, draw a second wave that's 180 degrees out of phase. Now, we can do this a couple different ways. Now, I've taught you a couple ways to do it, but I say find 1 wavelength. Here we go. The midpoint is going to be right here. So if I call 1 full wavelength, 1 full cycle, 360 degrees, half of it is going to be 180 degrees. So I can start right here. And I'm going to do the same thing. I took this wavelength and I'm just shifting it over 1/2 of a cycle. So notice if I start here, I go bingo, bango, and I'll come back here. And it's really just the reciprocal of this graph I've already drawn. So it should look pretty much like it in a mirror. And it'll look something like that. And that satisfies here. So wave A takes 4 seconds to complete one cycle, calculates period. Well, it tells me 4 seconds. Therefore, its frequency is 1 over 4, which is 0.25 hertz. Moving on to the next one. Let me get it in the middle. Here goes. A wave with an amplitude of 1.5 centimeters and a wavelength of 3 centimeters. So I'm actually going to be using each square to equal 0.5 centimeters. And you'll notice that these graphs are going to look a little different. And I actually have to extend this graph just based on the rules I gave you. So same rules apply. I plot my points, I put my dots, I did mine in black here. You'll see that I can just easily connect these. And it actually is larger because I had you doing, the graph I had you draw was a little larger than my margins, but oh well, I can creatively figure out a way. So the first one has a wave amplitude of 1.5 centimeters and a wavelength of 3 centimeters, a wave of an amplitude of 2.5 centimeters and a wavelength of 6 centimeters. So I actually did these out of order, but it's not the biggest deal. I'm just showing you how to draw both of them. So notice, and this takes me to my, let's see, so here's one, and I can go, let's see, 1, 2, 3, so from here, so 1, 2, 3, and 1, 2, 3. So here's my second wavelength. So okay, so my graph here looks like this. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Oh, that's my problem. This should come down to here. So what I have here is my drawing is going to look, they're going to look different because they have different rules in which they follow. They have the same scale, but the wave with an amplitude of 1.5 centimeters is only going to go up 3 boxes. The one with 2.5 centimeters is going to go up 5 boxes. The wavelength of 3 centimeters, notice it's going to need 6 squares total. So 1, 2, 3, 4, 5, 6. In this case here, my graph should look like, so 6 total, so it should end right here. Yeah, I knew something was up. Bingo. And it looks like that. So disregard that. But I'm too far in the screencast, and these type of screencasts I cannot go back. So this is correct. So a water wave has a frequency of 2 hertz and a wavelength of 5 meters. Calculate speed. Speed is frequency times wavelength. 2 hertz times 5 meters is 10 meters per second. Let's see here. Next one. Wavelength 50 meters per second, frequency at 10 hertz. Calculates wavelength. Well, lambda equals velocity divided by frequency. 50 meters per second divided by 10 hertz is 5 meters. A wave has a speed of 30 meters per second, wavelength of 3 meters. Velocity divided by wavelength. Right? I'm isolating these variables, so I'm solving for frequency. 30 divided by 3 is 10 hertz. That's its frequency. So a wave has a period of 2 seconds and a wavelength of 4 meters. Calculate its frequency and speed. Well, I know the period is given in 2 seconds. So frequency is going to be 1 over 2, which is 0.5 hertz. The speed here, calculate its speed as well. It says it right there. Make sure you're doing frequency. Frequency is 1 over t. Speed is going to be frequency times lambda, and my wavelength. So 0.5 hertz times 4 meters tells me my wave speed is 2 meters per second. A sound wave travels at 330 meters per second and has a wavelength of 2 meters. Calculates frequency and period. So the frequency is going to be speed, 330 meters per second, divided by wavelength of 2 meters is 165 hertz. And therefore the period is going to be 1 over 165, which is 0.006 seconds. And that concludes page 2. So moving on to page 3. So we're getting into some graphing here, a little bit more graphing. So I did these in advance. It's kind of hard to do when I'm talking you through them. So I figured I'd already have them done. So amplitudes are at the top, crests right here. My amplitudes are measured from equilibrium to the top, equilibrium to the bottom. It's simply the difference between the equilibrium line and the height of the crest or trough. Crests will be up here, troughs will be down here, and then wavelength. If you look at the original picture here, there were 2 total wavelengths in this picture. Here's one, and here's one. So 1 wavelength, 1 wavelength. So I asked you to draw something So I color coded these. So in phase and out of phase. So I think what's important for you to do is to associate that one wavelength. I'm going to set it equal to 360 degrees, because if it goes through one cycle, we can put this equal to a unit circle and say 360 degrees. So it's midpoint right here. I call 180 degrees. So I did 180 degrees out of phase in red. So I started here. I did the same thing. I essentially just shifted it over, and then I kind of worked backwards to fit it back. Blue, I had to do something a little different. I had to then subdivide 180 by 90. I shifted over only 90 degrees, and I completed in blue. And then black, I subdivided 90 by half, and I shifted it over only, in this case, 1/8 of the total, 360 degrees, and I shifted it over just a little bit. So black is labeled on there too. I think you can differentiate the colors on there in the video. I'll zoom it in. Okay. Moving on. Create a graph to scale. You can see that I set this one up here. Each box represents 1 centimeter. The wave has an amplitude of 4 centimeters, so 1, 2, 3, 4 is my amplitude, and a wavelength of 9 centimeters. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice my midpoint is 4.5, so I kind of missed it, but I was a little sloppy with my drawing. And let's see here. In a different color, draw a second one that's 180 out of phase. So I'm just going to use the original picture, and I'm just going to kind of ballpark this. And I'll just go through here. And it may not be perfect, but it should be pretty close. It's kind of the mirror reflection of it. So if it takes 4 seconds to complete one cycle, and calculate the period of frequency. Well, the period is 4 seconds, and the frequency is 0.25 hertz, 1/4. And then labeling your crests and your troughs, and let's see, one wavelength would be from here to here, and here would be a second wavelength. So one wavelength and one wavelength, and then here it says calculate period and frequency. So we already did that. The next picture we're looking at looks like this, and you can pause this at any point and kind of look if you want to just kind of see how to do the answers, because I think I'm going to run out of time, because I've only got like 2.5 minutes left. Okay, I only get 15 minutes on these. So here goes. The picture here looks like this. Come on, there we go. 180 degrees out of phase, I just drew the mirror image. 270 degrees out of phase, I went over 3/4 of the way, and I started right here, and then I just worked my way back. Okay, so how many wavelengths are in the picture? Well, if I look at my original, there's 1.5, so there's 1.5 total wavelengths. So if each wavelength is 4 meters, what is the distance from A to G? Well, it's one wavelength is 4, half of a wavelength is 2, so 4 plus 2 is going to give me 6 meters. There we go. So once again, 1.5 wavelengths in the picture. Which letter combinations represent a half a wavelength? Well, from A to C, we could say B to D, C to E, D to F, and E to G, and those are the only ones. So if the distance from A to G is 24 meters, and the time is 48 seconds, what's the size of one wavelength? Well, this is 1.5, so I could take 24 divided by 1.5, and I find it 16 meters. 24 divided by 1.5, 16. And the wave speed, well, if the total time is 48 seconds, I can take 48 divided by 1.5, and I find it's 32 seconds. So 16 divided by 32, speed is distance divided by time, is 0.5 meters per second. Let's see here. An oscillator here, I've got 1 minute left, so I want to make sure I power through here. 60 cycles in 1 minute, 60 cycles in 60 seconds is 1 hertz. And a wave on a shoreline arrives every 4 seconds. Period of 4 seconds, frequency of 0.25 hertz. Which in the picture has a greater frequency. The picture on the left, higher frequency, it has a shorter period, a smaller period. So in this case, shorter period, less time per oscillation, higher frequency. And finally, last page. So I'm going to scan this over. You can always kind of go back and look at it. And I didn't do all these labeling crests and troughs and amplitudes, etc. Wavelength, I labeled them. And the period is the time. So graphing here. If the total distance here, what's the size of one wavelength? It's going to be 6 meters. If it's 12 meters total, there's 2 wavelengths here. 6 meters. I don't know what I did there. 6 seconds to complete one full oscillation. The wave speed is going to be 6 meters divided by 6 seconds for 1 meter per second. And I will just show you these because I'm going to run out of time. So pause it where you need it.